Okay. Good morning. I'm, getting up at 9 o'clock for lectures is hard enough, but getting up at 9 o'clock on a Saturday morning, that is true devotion. Thank you for coming in. We're basically going to continue our discussion of BCS theory. And what I've learned from giving this course is that people want to, it's so important to understand this that people want to take their time. So we're doing that. And at the end, and only at the end, will I touch on the Coulomb interaction and say a few words about the journey that has been taken by the condensed matter community since the 1980s, okay? And the debates that are going on. We'll talk a bit about that, okay? So I left off on yesterday. We'd introduced the Bcs Hamiltonian. Let's write it down. It's extraordinarily simple form. It's just a cartoon, of course, but our Hamiltonian contained the electrons and a pairing term. And this pairing term here, A, creates pairs. And we were explicitly working with the understanding that this is in a narrow region around the Fermi surface. So our Fermi surface is a kind of Death Star in momentum space. It's got this intricate structure of up and down electrons occupying every single grid point in momentum space. Then we're thinking about a very thin atmosphere that lives like this, either side of the Fermi surface. Within a region of omega dBi. Remember, omega dBi is about 1,000 Kelvin. EF is conservatively 50,000 Kelvin. Okay? And we live at room temperature, which is 300 Kelvin, and BCS superconductors develop at 10 Kelvin. Okay, think of those hierarchies. And so this is really supposed to be a model that describes the low energy limiting physics inside this region, this narrow shell of momentum space. Okay? And remember, we're considering scattering pairs that start out at momenta minus k prime down, plus k prime up, and they're then scattering to another set of pairs at k up and minus k down. And that scattering process was described by an amplitude vk k prime, and we've taken vk k prime to be very simple, to be minus g naught over the volume, provided epsilon k and epsilon k prime are in this narrow atmosphere. Okay? And the logic behind this is that these are the electrons that feel the retardation, the fact that long after that electron has taken place, the contraction of the surrounding atoms provides this residual positive charge that attracts the electron that follows in its track. Okay? And so that's what we're discussing. Okay, any questions before we go on? So the idea that we had was that when we think about the fluctuation, we're going to be thinking about the gap, which is given by minus g naught over v times this summation over the expectation value of the pair operator. Okay? This is a mean field assumption. This is really the charge version of what Weiss and later Stoner introduced to understand magnetism. In magnetism, we understand that ferromagnetism occurs because each spin at each point of momentum space feels a Weiss field that is coming from all the other electrons that keeps it pointing upwards. Okay? This is a Weiss field, but in an unusual space. Instead of being in up and down space, it's in particle and hole space. And we're really going to bring that out today. Andrei Nevedomsky has alluded to that in his talk on topological insulators. I'm really going to try and make it very clear today. Okay? So this is a field that is intensive, but it affects all the electrons. And so as a result, when it fluctuates, when the long wavelength part fluctuates, that causes an extensive change in the energy, an extensive change in the action. And that extensive change in the action means that the probability, or more carefully, the probability amplitudes for fluctuations in the pair density involve an action of order V, which means they involve, as a Gaussian fluctuation, a sigma squared, a variance which is of order 1 over V. And so it's for that reason that we can ignore the fluctuations in A, or what we're going to do is we're going to expand this in fluctuations and throw away the terms which are of order 1 over the V down on the main terms. Okay? Condensed matter theorists today like to treat this kind of Hamiltonian within a path integral formulation. And the beauty of the path integral formulation is you really can treat these fluctuations as fluctuating variables. In a path integral, what you do is you replace operators by numbers, fancy numbers, but they're numbers all the same. And you really can think in terms of fluctuations of this variable delta. Okay? But since we're not using a path integral, we're going to use a more hand-wavy methodology based on operators, which is a bit more clunky, but means I don't have to try and go through all that formalism of path integrals in the meantime, which we haven't got time to talk about. Nevertheless, the idea is that we have this, we're going to try to calculate this Mexican hat today. Okay? And these are the amplitude fluctuations in delta. Okay? Okay, so let's look at that. Let's do that little expansion that we were thinking about yesterday. And we're going to take our minus G naught A dagger A over B term, and we're going to expand it. We're going to write this as minus G naught over V. I'm going to replace A by its average value and its fluctuation. Really, this is a tautology. I've written delta A is equal to A, the operator, minus a shift, which is its expectation value. Okay? Okay, thank you. All right. So now we're going to expand this thing out as a first term, which is just all the terms except the delta A squared. So we have and then the leftover term Now let's look at all these terms here, right? This Hamiltonian scales like the volume. It counts the total energy of the system, and so its expectation value is order the volume. This term here is also of order the volume, and the reason we've got the 1 over the volume here is because A and A dagger both scale extensively like the volume, okay? And so if we look at this term here, this term here, this scales like the volume. And we'll see that actually these terms here too, but this term here scales like, well, delta A dagger times A, that does scale like the volume, but divided by V, this whole thing together scales like order 1. Okay? And so this whole thing here scaling like the volume, and this term here scaling like 1, means that in a mean field theory, we can afford to neglect the fluctuations for the moment, okay? Just to get the leading order effects. There will be fluctuations, and in a real system, we will not have the luxury of this wonderful thing where every electron feels every other pair. This is just a toy model which we really can solve exactly. Okay, that's the important thing. If you prefer, we could also talk this being of order n and this being of order 1. Okay, because this is really volume measured in terms of unit cell size. It's a huge number. Okay, it's not 1 meter cubed, it's 10 to the 23 unit cells. Okay, is what it is. Okay, so because of that, we can now take this audacious step and throw that away. Okay, and now we can reassemble this. We can now rewrite this delta A in terms of our original operators. We only wrote it in terms of delta A just to get rid of the fluctuations. But now we're going to reassemble it in terms of its original form, so I'll rewrite this as A dagger minus A here, and this term here as A minus expectation value A. And when I do that, you'll see that I've got an A dagger A, but a minus A dagger A here and here. So 2 minuses and 1 plus give me a negative. A negative times a negative gives me a positive. And so when I'm done with all of that, this then gives me minus G0 over V times A dagger expectation value A plus expectation value AA. Okay, and then I've got left over plus G0 over V, I haven't made a mistake, A dagger A. Okay. And now I'm going to use this result here and just rearrange all of that. So this means this now becomes A dagger delta plus delta bar, which is the complex conjugate of A, times A, plus delta bar delta over G. Minus signs, aren't they always terrible? Just a second. That's good. Minus times minus equals plus. I'm good. Okay, good. All right. So that's my H, and now let's put it all in its completed form. This then tells us that our Hamiltonian, describing the motion of the electrons through this mean field, contains a term which acts on all the electrons. It's the kinetic term. But now a new term which we're going to have to discuss. I missed the volume here. This volume is there because delta is intensive, and so every term in this Hamiltonian has to be extensive, hence the V here. Okay? So that's our mean field term, and we're neglecting terms that are of order 1. Okay? In this expression. And that's what we've got to discuss. I'm told that the first preprint of BCS was sent to the institute that Bogolubov was working at. And he came over to the Landau Institute and he gave a talk on using his method, Bogolubov's method, to treat it. It was a re-derivation of the BCS results, and there was a young guy called Gorkov in the audience, and he had grown up working with Landau on quantum electrodynamics. He was familiar with the diagrammatic method, and they'd spent a lot of time adapting this diagrammatic method using a new idea that had come from Japan of using imaginary time, and they'd adapted it so that they could now deal with the electron gas and its interactions. But immediately he saw this thing, he thought, well, how can I use that method here? Okay, what does this mean? What's the physics of these funny things? Can I write Feynman diagrams to describe this physics? And so I'm going to share with you his line of thought now. Okay, so let's look at that. So this describes really two pieces of physics. Okay, and we're going to really focus on this pairing part here. This is H pair of K. Let's look at what that does, okay? And in particular, this term here destroys an electron, and this destroys an electron, and what is replaced by it is a condensate. So if we look at what this term really describes, it describes the creation of pairs, the creation and annihilation of pairs. And so I like to think of that as two electrons coming together, moving in opposite directions with opposite momenta, and then they're in some kind of equilibrium with the pair condensate. So we'll call this pair 2 minus. Okay? But there's a second process that is actually, in actual fact, the same process, which you can think of, because this operator here, C minus K down, okay, actually is a whole creation operator. When you destroy an electron with momentum minus K and spin down, what you're doing is you're creating a hole here, okay? And that hole at minus K down is actually a positive charge with momentum plus K and spin up. So you can think of this term here as actually creating a hole of momentum K and spin up. And this term here, it can be thought of as actually annihilating a hole, of spin up. Okay. And so that second term is what we call Andreev reflection. And this isn't because it is true that Andreev thought about this, and so he did reflect on it. But the reason we call it Andreev reflection is not because of that, but because of something rather remarkable about holes. Holes which have the same momentum as electrons actually travel in the opposite direction. Okay? And let me actually draw a picture now which illustrates that point. Okay, so if we think in terms of electrons, we're thinking in terms of this beautiful parabola of their dispersion. Epsilon k is E of k minus mu. E of k is measured from here, it's parabolic, but epsilon k is measured from here, which is the chemical potential. Okay, so this is epsilon k positive, this is epsilon k negative, right? And we all know that these are the filled states of the Fermi sea. But because they're filled states of the Fermi sea, what we often do is we like to think in terms of excitations. These are electrons moving to the left. These are electrons moving to the right. Okay? And remember that the velocity is d epsilon by dk. Okay? Or grad, maybe better to write it as gradient of k of epsilon. So here it's pointing to the right, here it's pointing to the left. Yep?
Sorry, just for the spins of the particle operator?
Yes, so it should be up and up. Yeah. They're all up, actually. Wait, okay. And so this particle hole transformation basically takes the filled states and flips them over like so. These are the holes here. Okay? This is the dispersion of the holes. The holes have energy minus epsilon of k. This is minus epsilon of k, okay? And notice that what I've really done here is I've taken this electron here, and I've written h of k dagger up is c of minus k down. So if I make a hole here, okay, I'm actually creating a particle. If I destroy an electron there, I'm creating a hole here. So the particle hole mapping does this, okay? In fact, when you do a particle hole mapping in the old way, you would just do this beneath the Fermi surface, okay? And so these guys travel to the left. Although their energy is positive, these are the excitations of the positive excitations of the Fermi sea, and they have the same momentum. They're on the right-hand side. They have the same spin, they have the opposite charge, and they have the opposite velocity. And so this funny process here, okay, which we can now represent in terms of a diagram. Let's look at this. This term is two electrons coming together like this, one at k up and one at minus k down, forming the condensate. And we're going to put delta here. When we draw a picture like that, we're using Feynman's kind of approach to physics, the idea that you can draw a cartoon, but you can also later on represent it by some mathematics, okay? And so we're going to write the math for this, and so I put the delta there to indicate that the amplitude for this process is delta bar, okay? But this process here is an electron coming along with k up, and now destroying a particle, and really we can think of it forming a hole traveling forwards is an electron traveling backwards. And so this is an electron traveling this way. It has momentum minus k going that way, and it has a spin down going like this. And this also has amplitude delta. Okay? And so this here is the Feynman philosophy as a whole. Of course, he invented it for positrons. A positron is an electron traveling backwards in time. So translated to the condensed matter context, a hole is an electron traveling backwards in time. Okay? And a hole is an electron traveling backwards in time. That sounds completely crazy. You may know that Feynman's advisor was Wheeler, John Wheeler. And after the, I guess, I'm not really sure of the chronology of this, may have been just before he went off to Los Alamos, or may have also been a little bit afterwards, but probably before. They used to meet on a weekly basis. It was very stuffy, old-fashioned style. Everyone wore jackets. You had to make an appointment with the professor. They still do this in Germany, by the way, without the jacket. And you had to come in there, and Wheeler was very particular about his timing. He had a clock. When you came in, it was like a chess clock. It started ticking, and you had half an hour. And when the half an hour was up, end of the discussion. Okay? So Feynman thought this was pretty stuffy. And also, there should be some symmetry in this relationship. So the second time he came along, he brought his clock. So Wheeler now had half an hour of his time, and click, started it off. They were discussing how to describe positrons. They knew of the symmetry between electrons and positrons. And Feynman was experimenting with an early version of his Feynman diagrams, and also they were playing with Green's functions, time-ordered Green's functions. And it turned out very nice to encode the propagators of the positrons as electrons traveling backwards in time. And the diagrams also worked out very nicely that way too. And so as the story goes, the week that Feynman figured out that positrons were electrons traveling backwards in time, he brought in his clock and he'd fixed it up so it ran backwards. Okay, so G. Okay, so when he started out, it ran backwards that week, and that was the little joke. Okay, but the basic point here is that actually, with this idea, you can kind of think that there's only ever one line of, in quantum electrodynamics, you could imagine there was only ever one electron in the world. And when that electron traveled backwards in time, it was a hole, a positron, and that we live in one slice of this world. And so when we see electrons and when we see positrons, it's actually just one electron in the whole universe taking its passage backwards and forwards in time. It turns out this idea doesn't work because of vacuum fluctuations, which also occur. And so, but it was part of the evolution, and it captures some of the creative spirit that was going on in trying to develop this new theory that combined electromagnetism with quantum mechanics, okay? And so all that aside is why you can draw the hole traveling backwards like this. And if you look at these two diagrams, you see that actually they're the same process. This is two electrons coming into the condensate, and all I've done here is draw it the other way around, okay? But this process is very interesting because it preserves spin, and it preserves momentum.
Sorry, I'm a little bit confused. Which of these lines is an electron, and which one of these lines is
The arrow is the electron moving forwards in life, okay? So here he is going forwards, and here he is going forwards, right? Okay? And so you can imagine this is going from time t1 to time t2, and this one also going from time t1 prime to t2, and they collide, and they both go into the condensate, right? But if I now take that same diagram and move t1 prime, so it's now in the future, and put t2 here, okay? Quantum mechanically, it's the same process, okay? I'm now propagating from t1 prime to t2, okay? It turns out that when you use time-ordered propagators, when this propagates backwards in time, it actually creates a hole, okay? And so from the point of view, if we don't say anything about the ordering of these times, they're actually the same process, okay? The Andreev scattering, however, going here, it's an electron coming in and it becomes a hole. And this process, as the electron comes along, you might think of it moving this way. It preserves its spin. It preserves its momentum, so it's a completely smooth process. No force is applied to the electron as it keeps going. But it changes, it reverses its charge, and it reverses its velocity. And it's this point that Andreev realized, okay? So actually, it turns out that you can actually do this at a superconducting normal interface. You can send in an electron like this. Here comes the electron. It forms the zero momentum condensate, and the hole comes right back like that. It bounces back like that, okay? And you can actually observe that experimentally. It's called Andreev reflection, and it's really weird because it time reverses everything, well, does what it does, okay? So it reverses charge and it reverses velocity. And by the way, it also preserves current, believe it or not, because an electron, a hole traveling to the left, actually has a current traveling to the right. Okay? So actually, this kind of Andreev reflection, when it's observed, actually doubles the current, okay, that you send in. You get an enhancement of the current. So this process here is completely adiabatic. It's completely smooth. There's no jolting at all. It's completely phase coherent, but it reverses the velocity, okay? And so that's kind of weird because in this region here, electrons are moving forwards, then they start to move backwards as wholes, then they're moving forwards, then they're moving backwards, then they're moving forwards, then they're moving backwards, then they're moving forwards, then they're moving backwards. They don't go anywhere. So their net group velocity is 0. And that's why this dispersion acquires a flat region, and you get a gap. This is called Zwitterbewegung. And it was first, the name, this wonderful name, was first given almost as a joke when the German community learned about this crazy new theory of this young guy, Paul Dirac, in the 1920s. Okay? And in the early days, Dirac's theory was regarded as an absurdity. It predicted all kinds of crazy things, negative energies, things going backwards and forwards, and all that. Anyway, this is exactly the same Zwitterbewegung that you have in Dirac theory, where it's electrons bouncing back as positrons, going forward as electrons. Okay? Yes?
Zitter, not spitter.
Thank you for this correction.
Zwitter is energy.
Okay, one more time. Zwitter?
Zwitter is neither female nor male.
Oh, that's kind of interesting, though. Kind of works. So it's kind of relevant to our time. Anyway, okay, good. Zwitterbewegung. Zitterbewegung. Got it right, okay? And so let's look at what this does. This, yes, sorry. Yes, here is our condensate already there, right? Okay, and so it's an elastic it's elastic, okay? That's the important. Elastic and phase coherent. So it makes sense. It's going to change the dispersion of the particle, change its velocity. If it's changing its velocity, it has to be changing dE by dk, okay? And so you can kind of see that it's going to introduce a gap. But let's try to understand. And that gap will turn out to be just delta, mod delta. Okay? Let's go and look at how Gorkov reasoned this out. And we can do it with just a few pictures. And that's what I like about it. Okay? And it's the joy of Feynman diagrams. If you haven't encountered Feynman diagrams before, the traditional way that they're introduced is in a big fat book of field theory. But this isn't how it was developed by Feynman. He developed it as a kind of tool, a shorthand to get rid of tomes of integral equations. Okay? And in the initial stages, he got it to work in the low energy, the low order perturbation theory. And then he said, well, since it works up to order perturbation theory alpha, or alpha, just up to order alpha, and we've got it all working there, leading order perturbation theory. Now let's just see what happens if we assume it works great to higher orders in perturbation theory. And we'll come back later, or we'll have someone else, and that someone else was Dyson, to figure out all the formulation and how it connects up with the Schwingerian, which is the operator-based field theory with integral equations approach. Let's take the Feynmanian approach now, which is really, in this context, Gorkov's approach, and let's write down Lev Gorkov's Feynman rules. Did I put the apostrophe in the right place? I think so. So according to the Feynman rules, when we want an electron to propagate from A to B, we associate an amplitude with it. But then it turns out easier if we change that amplitude by, rather than writing it as a function of x1 minus x2, we Fourier transform it in space, and we Fourier transform it in time, and then it becomes a function of frequency omega and momentum k. And we call it a Green's function or a propagator. And we use Feynman's picture like this. We give it a momentum, and we give it an omega. And the propagator for an electron in a Fermi surface is just 1 over omega minus epsilon k. And it turns out, remarkably, this has the Fermi surface encoded in epsilon of k, which is E of k minus mu, okay? And the poles of this thing at omega equals epsilon k give you the excitation energies, okay? So that's the propagator. So now you might ask, well, what about the propagator for a hole? Well, we represent that with the same diagram, but now the momenta minus k is flowing this way and minus omega is flowing that way, which really means k is flowing this way and omega is flowing this way. Okay? The energy of a hole is actually not epsilon k, but minus epsilon k. So you might guess, and in fact it turns out to be right, that this thing is just this. Technically it's epsilon of minus k, but that's the same as epsilon of plus k. How do you actually get that? Well, it turns out that that is minus 1, because the electron is an anti-commuting particle, and when you flip this thing round, you get a minus sign, because you've made the operators go in opposite directions. And it's a 1 over minus omega, because it's minus omega going that way, minus epsilon of minus k. So that's what it is, okay? So the Feynman rules for holes are that you give them propagators that look like this, okay? And now all we need to do is to add in the Andreev scattering. And so Andreev scattering says that when I have a process like this, I associate that with an amplitude delta bar. And when I have a process that is the opposite, I associate that with a delta. Okay? That's all you need to know to compute the Gorkov propagators. Okay? And so Gorkov said, well, look, now I want to calculate the propagator for a particle moving in the presence of Andreev scattering. So that's the propagator. And now we add in all the physics that goes in there. So first it goes along like this, and it comes out. Doesn't scatter at all. Second time it goes along, scatters off a delta. Let's draw it going backwards. A delta bar, and then it scatters again off a delta, and it goes on forwards. And then we can just do this many times. That's 1, 2, 3, 4. Okay? Delta bar, delta. I'm not even going to put them there anymore. Cross, 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 cross. Okay? Now you might say, well, what about the process that it goes and it comes back? Well, actually, that converts it to a hole. So I'm not going to think about that for the moment. And all these diagrams will straighten them out. You've got to do this an arbitrary number of times, plus dot, dot, dot. But it's much easier to write these by straightening the diagrams out. That's this one, plus this one, and now we come backwards and go forwards, plus the next one, backwards, forwards, backwards, forwards. Okay, and we can keep on doing this. Now, this process here is the minimal process when an electron goes into the condensate, flips into a hole, scatters again, and comes back as an electron, right? And so this process is something we want to focus on, and because it repeats, here it is, and there it is again. And if I do it several times, I can now put that process in an arbitrary number of times. And these little processes here, theoretical physicists call them self-energy corrections to the motion, okay? Because this part here needs to be described in terms of holes. It could be a more complicated process when we have interactions, but for our purpose, we're just going to write this thing as a Dyson, what's called a Dyson self-energy. Here it is. It involves the electron coming in here, scattering, going back, and we give this an amplitude. It's just this one has a delta bar, this one has a delta. So it has amplitude mod delta squared over omega minus plus epsilon k. That is our self-energy. It's a function of k and omega. Okay? And notice this thing has a pole at omega equals minus epsilon k. So it keeps the information of the hole that's there in the middle. So this describes a virtual process. The electron's coming along, it becomes a hole, but that hole has a different energy, so it doesn't conserve energy. It's a brief period of time it occurs. It's a virtual scattering process. This involves 2 Andreev scatterings. It's only degenerate, an on-shell, when epsilon k equals 0, when an electron can become a hole, can become an electron without any cost. Okay? But that's what it is. And so now we can look at this full Green's function here and write it very simply. This guy is G0. It's the original thing. This is the fully dressed propagator. So this fully dressed propagator, we can write it, we can now replace these terms here just by the self-energy term, sigma. And so this term here involves sigma twice. This one involves sigma once. Okay. And then we can just add all these processes up. They're very simple. In fact, you can see that this combination here, sigma times arrow, now occurs twice here. And it occurs 3 times here, and 4 times in the next one, and n times in the general one. And so this full propagator here can be written as G times G0 plus G0 sigma G0 plus ... G0 sigma G0 to the power R. In other words, this is G0 times a series, 1 plus sigma G0 plus sigma G0 squared plus blah, blah, blah. Okay? And that's just a geometric series. 1 plus x squared plus x cubed is 1 over 1 minus x. And so we can write this. We can write this G, curly G, as G times this geometric series. This is a geometric series. This is 1 plus x squared, which we know is 1 over 1 minus x. Okay? And, of course, the binomial expansion of this only works within a certain radius of convergence. So we're doing something kind of naughty here. We're going to use this inside its radius of convergence and then say, well, since it works inside the radius of convergence, it should work everywhere by analytically extending it. And therefore, the full answer, G, will be G, little g, over 1 minus G0 sigma, which I can then write as G0 inverse minus sigma, or if you like, omega minus epsilon k minus mod delta squared over omega plus epsilon k, all to the minus 1. Okay? Or if you like, you can write that as omega plus epsilon k over omega squared, multiplying that up, minus epsilon squared minus mod delta squared. And imagine Gorkov doing this in a seminar. There were long seminars in Russia in those days, usually 3 hours long. Okay? There's plenty of time to tune out, draw your diagrams, redraw them. And he came up with this, and he was delighted because he could see that here is the excitation energy of a Cooper pair, of a Bogoliubov quasiparticle. If we write E of k equals the square root of epsilon k squared plus delta squared, okay, you can see that this is G of k and omega equals omega plus epsilon k over omega squared minus big E k squared. Okay. You can also write it in another way, okay? One of the ways you can expand this is say, well, this is actually a complex function if you replace omega by z, and it has 2 poles. One pole at E of k and one pole at minus E of k, right? And so we can expand this out by expanding this around the poles. So the first term is omega minus E of k times stuff. And the second term is big E of k. And the second term is omega plus E of k times other stuff. Okay? And we can work out the other stuff by putting omega equals epsilon k into, we write this as omega plus epsilon k, omega minus big E, omega plus big E. Okay? And so if we put omega equal to big E here, the remainder is big E plus little e over big E plus big E. And so you can write this term here as half big E over 2 big E plus epsilon over 2e. And you can write this term as a half minus epsilon over 2e. And historically, this is called u squared, because this is nothing more than the u that appears in the BCS ground state, and this is vk squared here. And so this thing can be written as uk squared over omega minus e of k plus vk squared over omega plus e of k. In other words, when this electron starts propagating along, it can live forever when omega is equal to e of k or minus e of k. These are the excitation energies. If we now Fourier transform this back into time, we'll see that there are two components to the propagator. One at frequency plus e of k, one at frequency minus e of k. So going back to that picture that I had before, what we have here was our original spectrum of electrons. Here was our inverted particle Hall thing. And now we see that we've got positive energy excitations that look like this. And actually, we have down here their particle Hall transformation, which looks like that. Okay. Right. And so we can create particles up here. We can create holes down there, if you like. This is the semiconductor picture of superconductivity. But for the moment, just focus on these excitations here that we can see at omega equals e of k. And so this looks like our Hamiltonian has kind of got two kinds of quasiparticle. It has e of k with a of k and a of k, and then another one minus b of k minus b of k. And it turns out that these guys are the particle Hall transform of these guys here, and we'll see very shortly that this can be written as a of k up minus a of minus k down, a of minus k down, dagger. Okay, but for the moment, we're jumping ahead. All we've discovered is that this Svitterbewegung leads to a new dispersion of the electrons and the holes, which looks like this. And we've got to understand it, okay? And so we've seen that we've got a gap here. This gap here is mod delta, okay? And so when we create excitations above the ground state, they have this new dispersion, okay? Right? And so it's amazing because once you've got this, you've got all the key features of the phenomenology. You've got a complex order parameter. You've got a gap, which defines a coherence length, okay? What we've seen now is the effect of electron scattering off this order parameter, which produces pairing. Okay? Gorkov also realized that this process left out an anomalous process, which he could also write as a scattering process. It's the Andreev scattering. And the Andreev component of the scattering is a little bit weird. And he said, well, look, I don't know what this is, but let me give it a name. Let me call it F. It's the anomalous part of the Green's function. If I add an electron initially, and I take out a hole later, well, normally the amplitude for that is 0 in a Fermi liquid, because an electron can't convert to a hole. But inside a superconductor, an electron can give up its charge to the condensate and come back as a hole. It can Andreev scatter off the condensate, and that process is called F, and it involves an electron coming along and now scattering into a hole. The leading order process, this is delta bar, this is delta bar over omega minus epsilon k times omega plus epsilon k. But Gorkov realized he could actually do this repeatedly. He could do this one more time, like so. Okay. And you'll notice that coming in here is exactly the same set of diagrams I've already done. So I can repeat, I can put my self-energy here and do it twice, and then scatter at the end. So it's really an electron propagating plus an Andreev reflection at the end. And so this process here can be written as G times delta times omega plus epsilon k. Because this diagram and that diagram and that diagram are all the ones we've already calculated. In other words, this can be written as my original propagator times an Andreev scattering. And so actually, Gorkov was also able to calculate the anomalous propagator, and let's write them down. This is G. G was omega plus epsilon k over omega squared minus ek squared. And this one here, F, was equal to delta over omega squared minus epsilon k squared. It looks even more elegant than the first term. But they all have the same poles. They're all governed by the same quasiparticles. Okay? So that's what you can do just drawing pictures. In fact, very soon we'll see that these are two components of a 2x2 Nambu propagator. Okay? Okay, let's stop. Let's have questions. We have only half an hour to go. Will we make it? Okay. So, yeah.
The reason that you like to use single particle formulation to like a two-particle Green's function formulation here historical, or are you trying to make a larger point about reflection?
Well, I guess I was trying to show how just understanding the Andreev reflection and formulating it as an amplitude enables you to see completely how the electrons will propagate through this condensate. Okay? So we now really know the quantum mechanics of electrons moving through the condensate, albeit we know the amplitudes. Okay? We don't know how to make these electrons, how to write them down, and we're not really sure how to fully think about it. And so we've got ourselves to here, and we're running out of time, so we may only just about make it to here, but we'll see where we get to. Okay. But so the next part is I want to bring out this analogy between, okay, why have I done this carefully? Because every superconductor does this. This is, as far as we know, once you form a superconductor, all the detailed, fanciful physics about the glue, the pairing, the high-energy physics, whether it's a strange metal or a regular metal, whether it's phonons, whether it's magnetic fluctuations, whether it's RVB, okay? Inside the condensate, everything chills out, and it's just basically at low energies, electrons moving through this static condensate field, undergoing the Andreev scattering. What changes when I go to a more fancy superconductor, say a cuprate superconductor? Not a heck of a lot. The main thing that changes is that delta now becomes a function of k. Okay? So for example, and I think Giovanni will be talking about this, in a D-wave superconductor, this becomes cosine kx minus cosine ky. Okay? So instead of having a situation where the gap all the way around the Fermi surface is finite. Okay. In this situation, around the Fermi surface, the gap vanishes when kx equals ky, or kx equals minus ky. And so the gap changes sign like this, and the gap does this. The modulus of the gap goes like this. It's positive, negative, positive, negative. Okay? So this case has nodes in the gap. Okay? This case does not. These nodes are very, very important because they allow the scattering from here to here due to the magnetic fluctuations is repulsive. But this change in sign allows the condensate to trick the problem and use the combination of minor signs to produce the same effect as if the interaction were positive and there were no nodes. Okay? I don't have time to go into that now, but the point I wanted to make was that this basic formulation, once I replace this by delta of k here, and I write E equals epsilon squared plus mod delta k squared, works for all singlet superconductors, okay, of which we now have a great many of them, right? Okay. There's another conceptual point that we need to go over now, which is the analogy between particle Hall space and spin space, or the analogy between spins and pairs. And so that's our next point, spins as pairs. And in fact, it turns out that once BCS launched their theory, a great many people started to work on it, trying to develop new perspectives on what it really meant. And two physicists who were particularly important in trying to make this development were Anderson, working at Bell Labs, and Nambu, working at the University of Chicago. And Nambu had come in from particle physics, and Anderson had spent a lot of his early days working on antiferromagnetism. Okay? Nambu brought the ideas of field theory. Anderson brought the ideas of broken symmetry and antiferromagnetism, and the two came together. And so what we now like to do is I've already introduced the idea of a particle and a Hall operator, which is C minus K down dagger. And so when we do magnetism, we're very happy to introduce a two-component particle, which is CK up, CK down. We need that because when we have a magnetic vice field, it can spin flip from up to down. Okay? If the field points in the transverse direction, it can do that. And we're very happy to write the Hamiltonian then as psi k, epsilon k, and then if we have a field, minus sigma dot b, psi of k. That would be a ferromagnet. Okay? This is just the vice field. Okay? We normally put that in the z direction, but with doing it this way, we could put b in the x and the y direction as well. Right? If we did that, then it would couple, the bx would couple to sigma x, and the by would couple to sigma y. And let me remind you that sigma here is the Pauli matrix. It's sigma x, sigma y, sigma z. And just to remind you, that is sigma x is 1, 1, 0. Sigma y is minus I, 0, 0. And sigma z is 1 minus 1. Okay, so that's what this means. And we're not intimidated by it. Okay? So imagine if I replace the word sigma by tau. Oh my God, what does that mean? It's the same equation, okay? Right? It's just a change in notation, okay? Right? Excepting we're now going to do this for superconductivity. And in superconductivity, we want this to be the electron and the hole operator. But we write that as Ck up, C minus K down, dagger. Okay? Right? It has all the same properties as such a spinor. In particular, if I take psi k alpha with psi k prime beta, in both cases, it's an anti-commutator, which is 1 if k equals k prime and alpha equals beta, both for magnetism and for superconductivity. Okay. There is something a little bit funny about this. Whatever happened to the... these are both upspin holes. What happened to the downspin holes? What happened to the downspin particles? Where did they go? Okay, well, the downspin particles are actually hidden here. Okay, so we still have them, but we've actually, in some sense, chosen a special direction in spin space. If you want to fix that, you have to reintroduce the up and the downspin electrons and holes, and you have to go to a 4-component notation. But for most purposes, 2 components is good enough, unless you go to triplet superconductors where you have to put in the other things. And if you want to introduce a magnetic field, a Zeeman field, you also have to put the other guys in. But for most purposes, this 2-component, this is called a Nambu spinor, is perfectly good. It's terrifying because it seems to involve particles and holes, which we're not used to. But if once in the moment you think of it this way, it's no different, excepting one important thing. K here runs over all of momentum space, okay? Not just the bits inside the Fermi sea and the bits outside the Fermi sea. It's all of momentum space, okay? Right? But with this little trick, you can now transform the BCS mean field Hamiltonian into a form that looks just like the matrix expression I wrote down for a ferromagnet. And the only difference is that the direction of the magnetic field depends on momentum. And so if you had a weird magnet in which this depended on momentum, you'd have, in fact, a superconductor in some weird way, a weird kind of magnet. Okay? A superconductor is a ferromagnet in some sense with a momentum-dependent thing. In fact, we'll discover that this term is not even, that this term gets folded into there when we deal with these things here. So let's look at that, okay? Let's go straight to the chase and write down the Nambu formulation of the various parts. And I'm just going to use the blackboard to write it out in full. Here is my Hamiltonian. Now let's look at the ups and the downs. This is psi dagger of K. And then let's put in the downs and the ups. This is psi of K. Okay, now I've got to put the Hamiltonian in here. Okay, well, CK up, that's epsilon of K. Okay, now these guys here represent holes. Their energy is minus epsilon of K. Let's do it, let's guess it, but then let's reflect for a moment what we've done here. What we've done here, we've written E of K for the downs, like that, and then we've written it with a minus K here. Actually, I should put a minus K there to be C minus K down, C minus K down, just relabeling the minus Ks. Now we're going to interchange these two things. That now gives us epsilon of K. When I interchange these, I get a 1 minus C minus K dagger down. Okay? And here's the minus sign. So actually, if I really want to be strict, I've got left over a sum over epsilon K, which is a constant, which I might want to keep, but I'm not going to worry about. So now we've done the kinetic energy, right? Now let's put the pairing in. The pairing in, well, we've got the term that we need for our bookkeeping, V delta squared over G. And now let's put in the pairing. Well, the term that couples the C dagger is just delta, and this term here is delta prime, delta bar. So that's it. We've written it as a matrix, okay? And so the pairing terms are transverse fields in particle hole space, whereas the kinetic energy term is a Z component in particle hole space. There's a minus sign here. And in fact, if we write delta 1 equals delta bar equals delta 1 minus I delta 2, this minus sign for bookkeeping, then this whole thing could be written in a very elegant way as sum over psi dagger, k, epsilon k times tau 3, which is this term. And now the delta 1 comes in here. Delta bar is delta 1 plus I delta 2. And so this becomes plus delta 1 tau 1 plus delta 2 tau 2 psi of k plus v mod. And you can see that this is like a vector with 3 components. And so if we introduce h of k equals delta 1, delta 2, epsilon k, that's a vector in particle hole space. Okay? We can then rewrite this in the very compact form, psi of k, h of k dot tau, psi of k. And so, well, that's our Hamiltonian. And we can immediately start to use all we know about magnetism to understand superconductivity. And in fact, the better analogy is antiferromagnetism. So let's just write that neatly here and step back. We've got just 15 minutes, but we're going to admire it. We're going to write H equals, we're going to write it first this way. For most purposes, we can choose the phase of delta to be 0. And if we do that, we can throw away delta 2. Okay? That makes our lives much easier. So we'll often write this as delta 0 epsilon k. Okay? Then h of k becomes even simpler. We just throw this term away and throw out the just write it that way. Okay? But let's just look at this for a moment. Okay? It's very, very useful before you calculate anything to draw pictures. And I think to understand this, we're basically reaching saturation point in the lecture anyway. If we were Russians, of course, we'd be ready for a whole extra 90 minutes. You will have that, of course, but that's going to be a different guy. That's going to be Giovanni. He's going to come next, okay? But think of this as a vector, okay? Let's draw this vector. It's the direction of it. First of all, let's look at the magnitude of this vector. Well, it's just the sum of these 3 things. It's just epsilon k squared plus delta 1 squared plus delta 2 squared, which is nothing more than this. This is nothing more than E of k. Sorry, let me. It's nothing more than E of k, right? Now let's look at the direction of this thing. The direction, if we write h of k equals its magnitude, E of k, times a direction, n of k. What is n of k? N of k is just this thing divided by its magnitude. So it's just, let's write it out in full. I'm going to set E of delta 2 equal to 0, and we're now going to draw some pictures of this. So let's just do this. If I set delta to 0 altogether, I've just got a fancy reformulation of a Fermi liquid. So let's draw it for the Fermi liquid, and let's draw it for the superconductor. So these little directions, let's draw them, and let's just stop for a second, however. This is like a magnetic field, and I could write this as minus B of k dot tau. By analogy with electrons in a field, this is then a k-dependent magnetic field. And so the direction of that k-dependent magnetic field, if I write this B of k is minus h of k, which is then minus, well, it's just E of k times B hat of k, where B hat of k is just minus N of k. That's the direction in which the field points. Let's look at a normal state. Here is momentum space coming here, and here is the Fermi momentum, kf. Okay? So if I set in the normal state, I can just set these to 0, and N of k points up above the Fermi surface and down below the Fermi surface. So I'm going to draw my little ends of k's like this. These are the ends of k's, and my B of k points like that. That's my B of k. And B of k is the direction in particle Hall space that the state will want to go. So when B of k is up, this means that that particular momentum k will have a ck up, ck down filled state. Okay? But when it's down, it wants to point downwards, and so actually that state will be empty. And so you see that these fields naturally enable us to understand the Fermi surface. All the states are occupied here, all the states are empty here. The ground state of the Fermi surface is then just product over k less than kf, ck up, c minus k down. That's a Fermi liquid. Okay. But now let's go to the superconductor. Here's kf. Okay, and let's draw a little picture by the side to illustrate what the magnitude of B of k is, the magnitude of this field, which is mod E of k, which in this case is just mod of epsilon k. Well, that just looks like that. Okay, that's mod epsilon k. And this is nothing more than the excitation spectrum of the particles, the electrons, and the holes. Okay, this is near the Fermi surface. So now the superconductor, let's choose to turn off delta 2, make that 0, and call this delta. Okay? Now you see that we have a z component here and a x component. So very, very far away from the Fermi surface, the n of k points upwards, and the b of k points downwards, as before. This is little b of k. This is n of k. This is b of k. Okay? But now, as we come in towards the Fermi surface, n of k points to the right, so b of k actually points to the left. And you see, as we come along here, it gradually tips over until when we hit the Fermi surface where epsilon of k is 0, it's completely parallel. And now it's going to be coming all its way up. And so this is what the superconductor looks like in this pseudo-spin analogy. And so how do we understand that? At each point in momentum space, there's this field, and we can excite the system by flipping the pseudo-spin over and creating a state that looks like that. When we do so, we create two quasiparticles. Okay? And if we now look at this picture here, instead of having b of k, the magnitude of b of k being just epsilon of k, the magnitude of B of k is the square root of epsilon k squared plus delta squared, and it looks like this. And so this is the energy, this is delta here. And at this point here, it costs an energy 2 delta to flip this pseudo spin over. Okay? Anyway, so this is our Nambu state here, and I guess in some sense I've drifted, I've gone a little bit too rapidly. A spin up can be thought of as doubly occupied, and a spin down can be thought of as an empty state at that particular k. And so this state here has 2 electrons in it. This has no states in it. This is a pseudo-spin state. And if it's pointing at some angle like this, it means I've rotated that spin. I've got a linear combination of up and down. Okay? And so the ground state here at any particular point here would involve a linear combination of pseudo-spin down at k plus v of k pseudo-spin up producted over all k. But that's nothing more than a product over k times the empty state plus the occupied state So this is a pictorial way of understanding the BCS ground state. It is a domain in particle Hall space. A block domain wall in particle Hall space. And this picture is very useful to us because we can use many of the ideas of magnetism to understand this. For example, if I flick one of these spins, just flick it, it's going to vibrate and have collective modes. Okay? In fact, there will be one collective mode where I rotate all of the spins around this z-axis here, and it won't cost any energy. So if I rotate them differently at different places, there'll then be a sound mode that propagates, and that sound mode is called the Bogolubov mode. I can also use this methodology and immediately go crazy on the theoretical front. I can say, well, since this is a Hamiltonian that looks like h dot tau, I can write my Green's functions as 1 over that Hamiltonian, omega minus h, okay, h of k, which I can write as omega minus epsilon k tau 3 minus delta tau 1. And this propagator here is in fact the matrix propagator of the superconducting state. If you now write out the components of this thing, which you can do, and I'm going to stop at this point, you can then recover all the, you can then use this as a basis for many, many calculations. Let's look at what this looks like here. So basically, when you have a Hamiltonian, you can always deduce its eigenstates from the Green's function, which is omega divided by the Hamiltonian. I'm going to call this whole thing here h of k. Okay? H of k is just h dot tau. It is this epsilon k delta bar minus epsilon k. That's what it is. So this thing here says that g, the full Green's function, is omega times 1 is omega minus epsilon k plus epsilon k minus delta bar inverse. And if you invert that, its determinant is this times this minus this squared, which is nothing more than omega squared minus ek squared. And if then you rearrange, use all the things you know for taking the inverse of a matrix, you put A here goes down to there, and C here goes up to there, and these guys change sign. This is the full Nambu propagator for the superconducting state. This is the term we saw before. This is F, this is F bar, and this is G, called G bar. Okay? This is the propagator for electrons, this is the propagator for holes, and these are the anomalous Andreev scattering events. These Green's functions can be used to calculate, and once you use the Nambu formulation, when you draw an arrow like that, you really mean G. Okay? And so all the predictions of BCS theory can be done using the one-particle physics of these Nambu propagators. And so every prediction of BCS theory can be rewritten into diagrams made of these propagators. We've done no predictions, nothing whatsoever. This is where we've got to. Let's just end with one small thing that obviously comes out of this. If you buy, we haven't diagonalized this Hamiltonian, okay? We haven't looked at its eigenvectors, which the eigenvectors of this Hamiltonian H here are nothing more than the U's and the V's that we had at the beginning. Once we have those eigenvectors, we can construct the new quasiparticles that diagonalize this Hamiltonian. Okay? And one of the things you can immediately see is that you'll be able to rotate the basis so that this becomes diagonal. Instead of being h of k dot tau, if we change the basis, it will just become e of k minus e of k. And so when you work that all through and you rewrite this in terms of a new basis, a of k up, a of minus k down, which is projected, which is the original basis, psi of k, projected onto the eigenvectors of this Hamiltonian, they will then diagonalize that Hamiltonian, and this is then u of k, c of k up, plus v of k, c of minus k down. And you can work out these eigenvectors. These are the eigenvectors that point the pseudospin in the +1 direction. So once you have those, you can write this way. This is the Bogolubov quasiparticle. This is the bizarre quasiparticle, which is a linear combination of electron and hole, as it must be because it's Andreev reflecting, which diagonalizes the Hamiltonian. The Hamiltonian then looks like, in this basis, a of k sigma e of k times a of k sigma a of k sigma plus minus a half. It's kind of like a weird harmonic oscillator with a minus sign here, where these are the new eigenstates of the problem. Okay. What is the density of states of these eigenstates? We can work that out just by, and we're going to stop on this thing here. We know that dE times the new density of states of the quasiparticles must be the old density of states near the Fermi surface times d epsilon. And so that means that the density of states of these quasiparticles is the density of states of the original electrons times d epsilon by dE. But E is epsilon squared plus delta squared, and therefore little e, the original kinetic energy, is E squared minus delta squared, and therefore d epsilon by dE is E divided by E squared minus delta squared. And this is the density of, this then gives us the density of states of the superconductor, which is then E over the square root of E squared minus delta squared. This density of states and these unusual matrix elements are the core of BCS theory. And when you work through the consequences, they give rise to experimental consequences that can be checked. The most dramatic one is this bizarre density of states. Let's just draw it. It looks like a great big spike at the gap because all of the particles have been bunched up. This is what the original density of states looks like, n of 0. And this is what the modified density of states looks like. Looks like this. This is the energy. This is the density of states. And this is the gap. You can measure this in tunneling spectroscopy, and in the simplest superconductors, it falls on the nail with BCS theory. So if you send electrons into a superconductor, it turns out that di by dv at a voltage V is equal to or proportional to the density of states at energy EV. And so you literally get data points that sit on top of this at lowest energies. What you really see is something that looks like this, and when you plot di by dv. As you can see, I've struggled to get to the first prediction, and really it's just a first taste of the theory. What I've done in this course is I've given you an idea that at the macroscopic scale, superconductors can be described phenomenologically in terms of an order parameter. That order parameter is described by some kind of bosonic condensate. What we've seen here is that we can look inside the correlation length of that condensate, and BCS theory is a theory of the short distance physics. What we haven't touched on is the Coulomb interaction, and the Coulomb interaction can be reintroduced into this theory, and to overcome it, the condensate has to do somersaults. It has to do some funny things. It has to introduce nodes into the condensate somewhere. In BCS theory, that node is at finite energy. So the gap function actually changes sign as you go out to high energies to compensate for the fact that the interactions are repulsive at high frequencies and attractive at low frequencies. In high-temperature superconductors, the gap changes sign in momentum space in cuprate superconductors. We don't know where the node lies in the iron-based superconductors. We thought we understood the nodes of strontium ruthenate, but we're having to revise our understanding there too. And so in some sense, part of the phenomenology, part of the experimental search for what makes high-temperature superconductivity tick is understanding where the nodes of the nodes in the gap function lie in momentum space or energy space. We know where they are in high-temperature cuprates, but we don't know where they lie in many other systems. And even in the cuprates, we're not really sure that we understand the glue or whatever it is that keeps the pairs together. Some people even think you shouldn't think in terms of a glue, but instead you should think in terms of entanglement. You should think in terms of the parent state, which might be some kind of insulator with entangled electrons. This parent state, then when you dope it, provides the superconductor. And that's the link with the spin liquids that you'll be hearing about next week in Lucille Savary's talk. All of the interest in spin liquids has really spun off high-temperature superconductivity because of the thought that they might be connected. And if I'd had time, I'd have loved to have told you about what we're working on in iron-based superconductors. We're working on the idea that actually each individual iron atom with a strong Hund's coupling has a miniature triplet spin liquid sitting inside the tetrahedron. And that the non-symorphic structure allows this little spin liquid that's sitting inside each tetrahedron to escape into the condensate. So there's this big fight between spin fluctuation mechanisms and entanglement-based mechanisms, and where it will go, and whether it will describe this system or that system, whether it will help us get room temperature superconductivity. That's all part of the adventure that some of you are probably already engaged in. Thank you. And I'm around all of next week, so stop me and let's chat.